Okay, so we're going to go from atomic spectroscopy, which was electronic spectroscopy. We were looking at the electrons. And now we're going to try to broaden that into molecules. And this is where it gets ridiculously complicated. But like biology, it gets so complicated we can't keep track of everything. Okay, so it becomes easier because you just sort of draw cartoons. You don't actually draw the actual stuff that's going on. You know, if you look at the biology mechanisms and everything, they're like shapes. You know, enzyme, substrate, right? You can show the whole enzyme and the whole substrate and everything, but it's so complicated you can't really tell what's going on. So they just draw a circle with a bite taken out of it and stick a substrate in there. And that's kind of what's happening here with electronic spectroscopy. Okay, we'll start here with the oxygen atom. Here's the Grotrian diagram for the oxygen atom. It's crazy ridiculous. And then we can zoom in. That ground state, which looks like a single ground state, is actually 3 little ground states down here. This is a triplet P level and a singlet D level. And so let's talk about triplet and singlet. Remember, that tells you how many unpaired electrons you have. And so the oxygen atom, if we put those, we have the 1s2, and the way Gaussian calculates this, if you're going to have unpaired electrons, is it calculates the energies of each electron individually. And notice these pretty much have the same energy here. So that's the 1s1 electron and the 1s2 electron. So it's calculating in 2 different columns. These are the 2s electrons here. And then if we put both of those electrons in the P, the 4 electrons in the P subshell, and pair them all up, that's not the ground state. You know, Hund's rule said you keep a high spin first and then you start pairing them up. And we see that here in the Grotrian diagram. Down here is you put, all 3 electrons spin up in all 3 p orbitals, and then you add that 4th electron and pair it up. Now Gaussian goes ahead and calculates which one of those are. It put it in the px orbital. But that's where these term symbols come in. It could be in the py, it could be in the pz. And so there's a bunch of different ways to make this particular ground state configuration, and that's where we have these little splittings, those J values. And so so just with an atom it gets pretty complicated, right? And so this difference in energy, just pairing up that extra electron, if we just take this electron and move it over here, that raises the energy by 16,000 wave numbers. That's almost a visible transition. It's huge. You would think how small, what a small change. Well, it's quite a bit energetically. Okay. So we have this oxygen. This is that ground state electron configuration here, that triplet P for oxygen. If we take 2 of these and bring them together, we get the molecular orbital diagram. Now, we're going to have a whole section of the course on MO theory. And so this is kind of a chicken and egg situation. I want to talk about electronic spectroscopy, but you don't really know MO theory yet. But if I did MO theory now, you would kind of lose track of the spectroscopy that we're doing. So this year, and I change it up sometimes, this year we're going to do electronic spectroscopy first and then talk about MO theory. So I'm taking 2 of these atoms and bonding them together and making the sigma and pi orbitals. Now you do know sigma and pi from organic, right? And you should have covered a little bit of MO theory in your freshman course, although it depends on if people get there or not. Sometimes that gets pushed off the end of the semester. It just depends on who your professor is. You should have covered it in freshman chem. But do you recognize this little diagram here? This with the sigma and pi's here, and the sigma star and pi star. These are bonding and anti-bonding orbitals. And this is the ground state for the molecule. Notice the ground state of the molecule has 2 unpaired electrons. So what is its multiplicity? On the count of 3, everybody say it out loud. Its multiplicity, if it has 2 unpaired electrons, is 1, 2, 3. 3 or triplet. Yeah, it's a triplet. Yeah. So that is a triplet. So the ground state of O2 is a triplet. Okay. And that's, if we were to stretch that bond length, remember it's the electron cloud that holds the molecule together. So the electron cloud tells you what the bond energy will be. So if you change the electron cloud, you change the bond energy. If you change the electron cloud, you change the bond lengths and the bond angles. So the bond lengths and the bond angles are governed by that electron cloud because the nuclei hate each other. They would fly off into space if it wasn't for the electron cloud. So that's why MO theory is important. It tells you about all of the chemistry of the molecule and the atom because that's what the electrons are. Remember that 3s one electron on sodium, if the nucleus is in Huntsville, the 3s electron is in Argentina. So all the chemistry takes place with the electron cloud, that frontier of the electron cloud. You change just one spin of an electron, and you get different bond lengths, different angles, different bond energies. And that's what's being shown here. This is this is many of the excited states of the O2 molecule. This ground molecular orbital diagram and its population is this green curve here. And that's this triplet sigma G minus. That's the level there. This right here, what is this sigma and delta and sigma and all that business? That's Millikan notation. It's just for diatomics, because those were the first molecules that we worked with. They started using capital Greek letters, and then they realized this is unruly, and they went to A1, B1, A2, B2, AG, AU. And so this right here, these are Millikan notations. So you can put that on your notes here. We can circle these little guys here. Just don't circle the A and B. Just circle the Greek letters with their superscripts and subscripts. Those are Millikan notations. Bless you. Okay, and then this X state, that X is, again, electronic spectroscopy is really complicated, and so they just call the ground state X. I don't know why. That's what it is. That X means ground electronic state. And the lowercase and the uppercase A's and B's, I have no idea. I don't know why one's lowercase, one's uppercase, okay? But those are just sort of, there's the X state and the lowercase a and the lowercase b, and then there's the capital A and the capital B. No, don't know, okay? Yeah, so we have to look that up. But the main point I want to show is that for that ground state electron configuration in the MO diagram, that's what we have is the ground state potential energy curve. And some people for diatomics can write out, or they think this is a good thing to do. I think it's garbage, but so this says, for the 1 sigma, there's 2 electrons in the 1 sigma. For the 2 sigma star, there's 2 electrons, 3 sigma, 2 electrons, 1 pi, 4 electrons, 2 pi star, 2 electrons. And so they do these electron configuration things, but that is only going to work for diatomics. And since we're interested in more complicated molecules than just diatomics, why teach that? It's not really useful. So, but I would just show you that. You'll see that occasionally. Controversial statement, but that's what my opinion is. Now, what about this blue curves and yellow curve and red curve? Well, look at that. If you change the electron configuration, you get a different potential energy curve. And so if we were to pair those up in a different manner, in the pi star orbital, we'd have a different energy, different bond length, different bond strength, different vibrational frequencies. All of those things are affected by the electron cloud. The dark blue one, you could split it apart. Now notice all of those are, these are paired up. And because those electrons are paired up, they're singlets. See, it's a singlet delta and a singlet sigma. Okay. And so these are triplets, triplet sigma and triplet sigma, and so these have to be unpaired in some manner. So there you've got an excited state where that electron's in the sigma star. Ooh, I've got a mistake here. This little 4 sigma up here at the top should be a sigma star. I just missed the star. Okay, and then the red one is up here. This is, again, it's, there's no other way without exciting one of these further in electrons to get a triplet state. And so here I've taken one of these from the ground state and advanced it to the sigma star. And so this is, again, still a triplet because we have these two these two are unpaired. These two are paired still, even though they're, that's where that electron came from. It's still paired up. And so that's a triplet. It looks like there's a whole bunch of unpaired electrons, but no, these two are paired. And so it's just those two that are unpaired. So does everybody get the idea of this whole page? Is that if you change the electron configuration, you change the potential energy of the molecule. And notice here, the bond length for the ground state is whatever this tick mark is, right? So you come straight down, that's the bond length. So the bond length for the X state. But look at this one. Here's, just this grid line goes up here. Look how much longer the bond length is for this excited state, or for this capital B state. You see that the bond length is really stretched out because we've put an electron in an anti-bonding orbital, so we've weakened the bond. So it's natural that it would stretch out. We would have a much more gentle potential energy curve, and so we have a lower force constant. So the force constant is how wide this well is, and that gives you the different vibrational frequencies. Okay. And so this really introduces this term of potential energy surface. Oh, and this when these dissociate, these go to the ground state atoms. This goes to one ground state atom and one excited state atom. So that oxygen singlet D, that's the excited state oxygen. So this one will disassociate to an excited state oxygen atom and a ground state oxygen atom. So what do you think the difference between these 2 points here is? It's just the difference between this ground state oxygen and that excited state oxygen, and that was 16,000 wave numbers. And we're going to see that in our future lab when we do iodine. So even though this is the spectrum for oxygen, our iodine spectrum looks very similar to this, and we're going to see the differences in these potential energy surfaces. So you're actually going to use this in a lab, in the last lab of the course, this kind of diagram. So for a diatomic, it's a potential energy curve. You see, it's just a line that's a function of bond length. Energy is on the y-axis, bond length on the x-axis, and we call these potential energy surfaces typically, but for a diatomic, it's just a curve. But for larger molecules, it's a surface because you've got bond lengths, bond angles, and so on. And so you've got all of these different geometric parameters like lengths and angles, and you have an energy that depends on all of them. So we can only really visualize like two, x and y, like one is a bond length, one is an angle maybe, and energy on the y-axis, and that would give us a surface with the minima at the best angle and the best bond length. Okay, you get beyond two variables and it's hard to picture, but that's what we call it. We call it a surface, even if it's a complicated surface where you got 20 different geometric variables like bond lengths and angles, and the energy that depends on all of them. So this word surface is kind of a catch-all of this potential energy based upon all the geometric parameters of bond lengths and angles. So let's talk about the fates of excited states as we move from one potential energy surface to another. And so if we excite a molecule, because we're doing spectroscopy, it can change its bond lengths and angles. Just like if we go back, if we have a spectroscopic transition from the ground state here, it's going to go straight up because we hit it with light, and light is so fast that the molecule has no time to change its geometry. And so if we go straight up, we hit this potential energy surface there. And at that wavelength, we've given this molecule enough energy to disassociate. It will come down here and leave. So we will break that molecule apart because we went straight up and hit that potential energy surface, and then it's going to dissociate because we've given it enough energy. Some molecules, we get up there to a bound state. But notice how these potential energy surfaces are kind of touching. They're touching on this end, they're touching way up here. And molecules, let's say if it's in this vibrational state here, it can jump from this vibrational state on this potential energy surface to one that's lower. And so it can hop from one potential energy surface to another. So how does that work? Well, it stretches its bond or compresses its bond until it's at a place where the electron cloud can flip or change. And if the electron cloud flips or changes, at that point, there's no energy difference because those surfaces touch there. It's at a particular geometry where the surfaces cross. And so you have this instant change in the electron cloud, and that puts you on a different surface. And now you can get lower in energy and relax. So that's these fates of excited states. If we excite a molecule, it can move from one potential energy surface to another with the same multiplicity, and that's called internal conversion. So these are vocabulary words on this page here. Internal conversion. And so focus on internal conversion goes with the same multiplicity. So those two things have to be connected, because intersystem crossing is movement from one potential energy surface to another with a different multiplicity. So here we've had a spin flip. So we have a geometric oscillation, a vibration, and then the molecule is at a particular place where two potential energy surfaces have the same energy, and a spin flip occurs. And now it's on a lower potential energy surface and it can relax. So these are both non-radiative relaxation pathways. So you can hit a molecule with light and it can relax back to the ground state sometimes without giving you light back. Then we have dissociation. What I just showed you earlier, where the light went up and it hit that red curve way above its bound state and then the molecule just falls apart, that's dissociation. So electronic excitation to an unbound potential energy surface, or giving it enough energy to exit its potential energy surface. It's kind of a contraction. It's dissociation, but we just say dissociation. We just drop the A. And then predissociation. This one's a little strange, but some potential energy surfaces are bound. All the ones we saw earlier have a dip in them where the molecule can kind of get trapped in that valley. Some of them don't have that. They just don't have a dip. They just go straight out and they're unbound. And if you're in a particular geometry where your potential energy surface crosses an unbound one, you can have internal conversion or intersystem crossing, and then you can be on an unbound state and the molecule just falls apart. So we'll look at all of these individually here coming up. But this is just a nice page that has all four of these vocabulary words on it. So let's think about if we excite a molecule and it wants to emit light, there's a couple of different ways it can emit light. So fluorescence, that would be singlet to singlet emission. I guess it could be triplet to triplet as well, so we can put that in too. The main thing is that there's no change in spin. It's going from either singlet to singlet or triplet to triplet. So these are two potential energy surfaces, and it's emitting light. So it's jumping from one to another. They're not crossing. It's just jumping from one surface to another and spitting out a photon of light. And if it's a spin allowed like this, these are allowed, so they're fast. But if it's a singlet to triplet or triplet to singlet, then that's called phosphorescence. So fluorescence, there's no change in spin. And phosphorescence, there is a change in spin. And so this is, let me explain what these curves are. So we're hitting this molecule with light, and we see that light's coming out of it, and then we turn our source light off. And then the light that's coming out of our sample drops off. And if it's fluorescence, that drops off very quickly. So you flash light on it and turn your light off, and then the light that's being emitted from that substance drops off very quickly for fluorescence. But for phosphorescence, it can last a long time, up to minutes. And this is the glow-in-the-dark stuff. So I'll put Halloween on that. That's what makes Halloween fun, is glow-in-the-dark stuff. Okay, and so that's because it's forbidden. It takes a long time for that light to leak out. And so that's what I've got here. So the bottom one is loud. It's very fast. And the top one is forbidden, so it takes longer to happen. So, symmetry and angular momentum and everything tells that molecule, you can't do that. And so the molecule says, hold my beer and watch this. So statistically it'll happen, but it's really slow. Okay. So let's talk about the combination here, the non-radiative relaxation and radiation. So if we have absorption, so I'm showing two potential energy curves. So we'll show most of our diagrams as diatomics, but you could picture this being a surface with two little dips in it. And so you could have an excitation up to the surface and it finds its way into this dip. That would be the radiationless decay. And then it would eventually spit out a photon and drop back down. Okay. So these blue arrows, this is light, okay? Indicate light with H nu. Okay. Now you say, well, wait a second, you can't, energy is neither created nor destroyed, right? And so this up here, we call this radiationless decay. It's really heat, okay? It's light too, but we don't talk about it as being radiative. I don't want to confuse you. We say it's non-radiative because we're looking in the visible region or the UV region. And so we don't see that because it's coming out in the infrared region. So they used to call this radiationless decay, non-radiative decay, but it's infrared. And so it's, we'll just leave their terms alone. It's non-radiative, but we know that heat coming off that sample is very low energy radiation. Now here's an example of intersystem crossing. So we have absorption. So light comes in, excites our molecule to these singlet states. So it's singlet to singlet, right? So it's going up to singlet, and then it transfers here with ISC to a triplet state. And that happens right here where the geometries match. So when it gets to this bond length, notice how both potential energy curves touch. And that's when this electron will flip a spin and go from paired to unpaired. Because remember, the lower energy electron cloud has a high spin. And so a lot of times this happens. You get a singlet to singlet absorption because that's allowed. And then the geometry starts to relax a little bit and you get intersystem crossing and it jumps to a triplet surface. And it finds itself down here in the ground state of this triplet potential energy surface, and it's kind of stuck there until some quantum event happens and it can spit out a photon through phosphorescence. So notice this is phosphorescence and this is just fluorescence. I want to pause and make sure if there's anything you need clarified, I will clarify it as we go along. Okay. So this is using lots of different terms. Absorption, emission, you've got those. That's old school. Radiationless decay, that's going down through the vibrations. So it's just vibrational relaxation, spitting out infrared photons or, if it's a more dense sample, collisions. But we're really dealing with gas phase molecules since we can understand them the easiest. So these are little infrared photons coming out, which we don't see, so we call it radiationless. And then we have fluorescence on the left, and then over here we have that intersystem crossing where there's a spin flip, and then phosphorescence. That's allowed fast, and that's forbidden, so it takes longer. Same kind of thing. Now this is dissociation versus predissociation. So in the spectrum, so this is our spectrum here on its side. So if you look at that sideways, you see a bunch of bumps, and this will be like the visible spectrum, so I'll say visible. And we're going to see this in the iodine spectrum. We're going to see lots of peaks. These bumps in that spectrum, see what they correspond to? They correspond to the vibrational levels. That's pretty cool, isn't it? So here we have electronic spectroscopy, and we're resolving the vibrational levels. So it's also vibrational spectroscopy. And so they combine and call it vibronic. Just like we had rho vibrational, now we have vibronic spectroscopy. So we're seeing vibrations and electronic transitions on top of each other. And so whenever that photon of light has the right energy to kind of hit one of these vibrational levels, then we have a higher probability of it being absorbed. And so we have an intensity jump. And then when it goes between those levels, we have a dip. It doesn't go to 0 because we also have rotational lines on there. So there's little rotational lines on every one of those vibrations. And so we just can't resolve the rotational lines with our normal spectrometers. You can get in there with some really high resolution lasers and you can see the rotation change and the vibration change and the electronic change. And so you can do rho vibronic spectroscopy if you have an ultra high resolution laser. And so we don't have anything that high resolution in the department. Then notice how these lines get closer together, and then we have a continuum. This piece right here to there is a continuum. Okay. Meaning there's no vibrational changes, right? We don't see any kind of vibrational changes. We don't see any bumps from the rotational lines. It's just smooth. And what's happening there is, notice if I have a molecule that happens to be compressed when I hit it with light. So this molecule, this little wave down here is the vibrational wave function. Which the ground state vibrational wave function is a Gaussian shape. So that was my attempt to make a Gaussian shape. I wish I had a ruler on here. So if the molecule happens to be compressed when it's hit by that photon, and that photon has a high energy, it's going to hit this potential energy surface up here. And notice how that gives the excited state molecule enough energy to dissociate. And so you can kind of think of this as if I put a ball on this hill right here, it's not going to be bound, is it? It's a carnival game, right? It's going to roll down the hill. If it stays in the well, you get a prize, but it's way too tall. And so it's going to roll out here and be gone. So that's dissociation. You've given the molecule too much energy, it rolls through the pit and comes out the other side, and the molecule is broken apart. And there's no real difference except, if I give it this much energy, it just comes apart with less kinetic energy. If I give it this much energy, it comes apart with greater kinetic energy. So the difference in those absorbed photons of light is just different kinetic energy of the atoms flying apart. But if I'm below that dissociation limit, then I'm putting the molecule in particular vibrational levels, and it's bound. If I come up here and I put that ball right there, then it's going to oscillate back and forth. You can think of it in this physical manner where it's just oscillating back and forth in that bound well, and that's the vibrational wave function that you see. So that's the one on the left, dissociation. Once I get above a certain energy, then I'm breaking the molecule apart. And you'll see that in the iodine lab. You'll see these peaks get closer and closer together from anharmonicity, and then it'll be a continuum. And then you're done. Now, sometimes you can have this crossing of an unbound potential energy surface. So here I give the ball this particular energy, and this really is the carnival game, right? You give it that much energy, it goes down here, it does an intersystem crossing and goes out this way. And so there, I didn't give it enough to dissociate with the photon, but because of this either internal conversion or intersystem crossing, it hops on another surface and exits. And it's particularly profound if you give it an energy that's right at that spot. So right around this spot, if I were to give the balls this much energy, then I would have a higher possibility of having that crossing state and having predissociation. Now, how do we know when predissociation occurs? We see these missing vibronic transitions. So over here, we had this nice progression. We saw every little vibrational peak. And over here, we see a couple of vibrational peaks. And then there's like some missing vibrational structure, and then it picks up again. And so that's how they discovered this process of predissociation. And it just gets more and more complicated. So that's as deep as we're going to go in sort of these crossing things. But that's an interesting thing. We could look at these vibrational states to kind of learn about our excited states in our absorption spectra. And so this is one last thing to point out. These are absorption spectra, visible. Let me write it over here. Absorption. And absorption spectra tell you about the excited states. I think there should be a C in there somewhere. Okay. Can you tell? Can you see that? We're doing absorption spectra and we're learning all about the excited states. It's where the molecule is going in the absorption spectra. It's the emission spectra that tell you about the ground state. We'll see that in a minute. Okay. But can you see all those vibrational transitions and so on in the absorption spectrum are primarily they're telling us all about the vibrational structure of the excited state. All we know about the ground state is really very little. We've got just this ground state wave function and that's it. We don't know really anything about the ground state. So here, absorption, again, what I just said, characteristic of the upper state. So these are the vibrational spacings of the upper state. So that's this, if we've got V prime equals 0, V prime equals 1, V prime equals 2, 3, 4, 5, 6, 7, 8. So I've labeled all of those levels. And so you could see that 0 to 0 transition. So down here, this is V double prime equals 0, 1, 2, 3. So the 0 to 0 transition is right here. If that molecule happens to be a little stretched when you hit it with a photon of light, you could get it to go vertically straight up from 0 level to 0 level. Make sense? And then this maximum right here, this is the ground vibrational state, and its maximum is right below state number 6, it looks like. 5 or 6. And so the tallest peak up here should be 5 and 6. 5 or 6. And that's how you know the relative positions of these potential energy surfaces, is to look what your maximum intensity is for absorption. So does everybody understand the absorption curve? These are the vibrational transitions in the upper state. Now let's look at fluorescence. We have radiationless decay, so it rattles down. You ever see that game Pachinko? Okay, that's the way I think of this radiationless decay. You're shooting these pachinko balls up into the upper state and they're rattling down through all the vibrational levels. If you could get into a molecule and listen, I bet it would be ridiculously loud, He's hopping through all of these vibrational levels. Of course, they probably don't make noise, but in my imagination, it's like a pachinko game. My cousin had one that he got for Christmas when we were little kids, and it was the loudest machine I've ever heard, because all these steel balls banging against the glass. It's ching, ching. If you haven't seen pachinko, Google it. It's great. Okay, so the way the Japanese have gotten around gambling. Okay, so it's like our slot machines. So you go in and you can't gamble, right? So you come in with your steel balls and you put them in the machine and you play and they fall in the right little holes and you get more steel balls. And so that's the currency in the pachinko parlor. Next door, that person's cousin is buying and selling steel ball bearings. Okay, so you go over there and you're like, I got 5 pounds of steel ball bearings, and they're like, okay, I'll give you $20 for that or whatever. And so it's been, that's their little gambling slot machines. We do the same thing for kids at Incredible Pizza. It's little tickets. So then it pachinko's its way down here to the radiationless decay, and now it's in the ground state of the excited electronic state. So the ground vibrational state of the excited electronic state. Does everybody understand the careful terms there? Okay. And if it's compressed, can go straight back down to the 0 to 0 transition. So that 0 to 0 transition can have the same wavelength. Okay, but it's not the most strong peak because, again, there's not many molecules that are that compressed. Most of the molecules are right here in the middle because of that vibrational wave function. And so the strongest peak should be the V prime equals 0 down to V double prime equals 1. And so this picture is not quite accurate. This should be the strongest peak here, the 0 to 1 transition. So this one is V prime equals 0 to V double prime equals 1. Okay, and this one here is V double prime equals 0 to V prime equals 1. You see, the primes are important, aren't they? Okay, and you'll find that out when we do the iodine lab. It's exactly this. So notice that this vibrational spacing here is characteristic of the lower state, lower electronic state in those lower vibrational states. Now, this is something that may not be as obvious to you, but the overlap here, this is like the only the only frequency that can overlap in these, because there can't be a longer wavelength absorption. Remember, the shorter the arrow, the longer the wavelength. So this is the longest wavelength absorption. Can you believe that? Like, look at that until you convince yourself that that makes sense. That's the shortest arrow that you can have of absorption. And shorter arrows are longer wavelengths. So that's the longest wavelength absorption that you can have, is the 0 to 0. Make sense? Ready? Okay. Now let's look at the emission. Okay. That 0 to 0 is actually the longest arrow that you can have in the emission. All of these others are shorter arrows. And so this is the shortest wavelength of emission. And I'll point not to that one, but to this one. Like if this, so this 0 to 0 going down, that's the longest arrow that you can have. And so that's the shortest wavelength of emission. And so the fluorescence is got, the shortest emission is the 0 to 0, and the absorption is the longest wavelength is the 0 to 0. And so you have absorption is always to the blue side, and fluorescence is always to the red side. Fluorescence is the shorter absorption is the shorter wavelengths, and fluorescence are the longer wavelengths. Okay. Okay. So this is an important slide, and you can go back to the video and listen carefully to what I said. Now, these intensities of those vibrational transitions follows essentially, the guys called it the Franck-Condon Principle in their paper. Franck-Condon wrote about it, but it is sort of an approximation to the transition dipole moment integral. It's the wave functions times each other. They're missing the piece in the middle that has light. But if the wave functions overlap really well, then you're going to have a higher intensity. If they don't overlap very well, you're going to have a lower intensity. And so it's essentially a piece of that transition dipole moment integral. Notice I've been drawing my transition arrows straight up. They call them vertical transitions. Because light's so fast, there's no time for the bond to stretch while light is being absorbed. So think about this. If I'm in this molecule, this is my structural parameter. This is the internuclear distance. For me to go diagonal here, what has to happen? My bond has to stretch at the same speed as light coming in and interacting with the molecule. That can't happen. And again, that Born-Oppenheimer approximation. Remember the gnats and the guy trying to get away from the gnats. So this can't happen. I'm going to put a big X there, because that's not a vertical transition. That's going diagonal in this potential energy surface. So the geometry is fixed whenever light is being emitted or absorbed. Those are vertical jumps. So let's get to now the name of the lecture, the Jablonski diagram. These curves that I have on the left are only really drawable for a diatomic. And so even if we go to a triatomic, now we've got 2 bond lengths and an angle. And so we've got 3 geometric parameters and energy. So that's a 4-dimensional plot. We can't even do a triatomic. So what we do is we kind of punt. We take this ground state and we just draw a bunch of vibrational lines. Not even accurately, we just draw a bunch of lines in a box. Okay, so that singlet 0 is the ground state. This big singlet here, we call that singlet 1. So we just label them 0, 1, 2, 3, 4, 5, all of the singlets labeled with an S. And then we have a triplet, and that's the green. So this thing on the right on the screen is the Jablonski diagram. You see how it just simplifies things. And then we label these arrows like inter-system crossing here, or internal conversion. So internal conversion goes singlet to singlet. Inter-system crossing goes singlet to triplet, or triplet to singlet. And then the radiative transitions are phosphorescence and fluorescence. They're labeled there. So let's sort of walk through all of these different paths. We have blue light absorption. That's the pump. That's the hitting the bar on the pachinko game. The ball's thrown up the top, and there's a lot of things that ball can do. It can go down different holes or bounce off the pegs. It can go up and it can relax non-radiatively till it gets to the bottom of that surface, and that's our non-radiative relaxation. It can do an inter-system crossing and go down in the triplet state and relax a little bit and give off some IR. And it can do an internal conversion, hop over to the S state and relax all the way to the ground state. And that's a real boring molecule. You hit it with light and it just heats up. It doesn't give off any fluorescence or phosphorescence. It's not very good for Halloween. Okay, but it could, if it gets to the bottom of those other states, it could emit a photon, spin singlet to singlet, and be fluorescence, or triplet to singlet and be phosphorescence. Okay. So that's the Jablonski diagram, and that's sort of, we went through the diatomic potential energy curves, and then we simplified things, and there's really not that much, not that much complication to the actual diagram. This is just talking about the things that absorb light. So these are in your notes. You can look at them. You've learned some of this from organic, pi to pi star transitions into pi star. So we call them chromophores because chroma being color, these are the functional groups that give us colors in visible spectra. And here's, you could maybe attempt to figure out a structure of a molecule based on the UV vis, but it's pretty garbage because the peaks are so wide and broad. For structure, you're going to need infrared and mass spec. If you give me infrared and a mass spec, I can tell you what the molecule is. And then this is just showing the color of different azulines. So this is a spreadsheet that I built to look at molecular color. And so these are the different colors that you get with the different functionalization on azulene. Now this is azulene, and it's called azul because it's blue. Okay, and then you put different things on it and you get different colors. So that's pretty. So this is using your color lab information and just kind of flexing a little bit. So y'all have a good day.